So now, in this example, we are going to fill out this table. Now, these tables are somewhat similar to what you might see on the exam, where it's going to ask you for lots of different components. It's going to ask you for a Lewis dot structure, a VSEPR structure, to name the base and the molecular shape, draw the dipole for the bond. Is the bond polar? Is the molecule polar? This is going to take a second for each one. So we have 5 examples. They are all quite similar. So first, we want to calculate the valence electrons. So for arsenic tetrahydride or trihydride, we have 5 plus 3. That gives me 8. The underlined atom goes in the center. So we're going to connect our 3 hydrogens. Hydrogens have a full octet or a duet at 2, so we have 2, 4, 6. The last 2 go here. So that looks good. More often than not in Gen Chem 1, for a neutral atom, there are no charges. So, but you should always check. I have checked. They are neutral. So now we want to draw the VSEPR structure. And so when we look at this structure, we can see that there are 1, 2, 3, 4 things connected. That means our base is tetrahedral. And so now I'm going to actually zoom in on these just to give it a little bit more space. We're going to put our arsenic in the center. I'm going to draw a tetrahedral structure using wedges and dashes. I'm going to put my 3 hydrogens on. It does not matter where they go. And then we have a lone pair. Again, we show all of our lone pairs in this course. So the molecular shape is trigonal pyramid. So the electronegativity for arsenic, so the ASH bond is 2.0 minus 2.1, and that is nonpolar. And so then the molecule is also nonpolar. Although the electrons do allow you to have some polarity, in terms of this, the answer is no. Hybridization is based on our base geometry. So everything that is base tetrahedral is sp3 hybridized. Hybridization feels really complicated, but if we remember that if we can figure out the base geometry, we can identify the hybridization. So up next, we have XEF4, yeah. So the valence electrons here are 8 plus 7 times 4, and that's going to give us 36. So I'm going to put my xenon here in the center. I'm going to connect my 4 Fs. Per the rules, I'm going to fill all of their octets. So now I have used 32 of 36 electrons, so I'm going to put the other 2 here. So if we look at xenon, there are 8 compounds around it, or no, I'm sorry, there are 6 things around it. That gives us base octahedral. So we can start by drawing that. Sorry, I forgot what was happening. So this is how an octahedral molecule looks like. So we need to ask ourselves, where do we put the fluorines? The fluorines are all equivalent, so it turns out they're going to all go in the center. So we're going to put our fluorines here. Then we're going to draw all of our lone pairs. And put our other 2 lone pairs here, and so this is square planar. So now we want to ask ourselves, is this bond polar? So the XEF bond, so xenon has an electronegativity of 2.6 minus 4, so it is polar, and it's going to go in the direction of this. So we have 4 polar bonds, but they are all equivalent to each other. So the molecule is not polar. So then we ask ourselves, what is the hybridization of this central atom? And it is sp3d2, because everything that is base octahedral is sp3d2. So next, we have formaldehyde, which has 4 plus 6 plus 2, so that's 12 valence electrons. So we're going to put everything in the middle. I'm going to put a hydrogen here, and an oxygen here. So if we do this, we have used all of our valence electrons, but not everyone has octet. So I can remove these two and give a double bond here. So now everyone has octet. If you were to check the formal charges, all of these compounds do not have formal charges. In the previous structure that did not have octet, there are some of those that do have formal charges. It is an invalid structure, but it is a possible structure. So from here, we need to ask ourselves how many things are connected to carbon, and that's 3. So that is trigonal planar. And so we're going to put our carbon in the middle, and those are at roughly 120 degrees. And so we see this, and the shape is also trigonal planar. If it asks you for both, you need to indicate that it is both. If you only provide one answer, I assume that you do not know the other answer. So you can write trigonal planar for both. There are lots of ways you can write that down. So let's look at we have a carbon-hydrogen bond. We have a carbon-oxygen bond. So if carbon has a 2.5 minus 2.1, 2.5 minus 3.5. So this is nonpolar, this is polar, and it goes in this direction. And overall, the molecule is also polar. So we ask ourselves, what is the hybridization of the carbon? And because it is trigonal planar, has a steric number of 3, it is sp2. You should ask yourselves, what is left over? We have a single pure p orbital left over on the carbon. That leads to our pi bonds that we can observe. So for our next one, we have a charged compound. So we have 5 plus 3 plus 7 minus 1. So when it is positive, we're going to take away an electron. So that gives us 14. I'm going to put my phosphorus here in the center, put all of our friends around it. So we've now used all of our valence electrons, and everyone has octet. This looks good, but we know that the molecule has a charge. So who owns the charge? So the formal charge for chlorine is 7 valence electrons minus half of the bonding electrons, which is 2, minus all of its lone pairs. That's 0, so not that one. For phosphorus, we have 5 minus half of 8 minus 0. That equals 1. So we know that phosphorus is going to have a +1 charge. So now we've identified our charged molecule. So we need to ask ourselves, what is the shape here? The phosphorus has 4 things connected to it. That means it's tetrahedral. And so we can draw that structure here. And so it does not matter what goes on each one because they're all equivalent. And our positive charge still remains. And so in this one, both the base geometry and the molecular shape are tetrahedral. So now we want to know, are the bonds polar or nonpolar? So for phosphorus Cl, the electronegativities are 3 minus 2.2, yes, and they go in this direction. So chlorine is more electronegative. Then phosphorus hydrogen is 2.2 minus 2.1, and this is not. So the molecule is slightly polar. So when we look at polarity of molecules, we want to think about the direction in which it pulls. So in this case, the phosphorus hydrogen bonds are not polar, but the phosphorus chlorine bond is. And so we have an overall polar molecule. And what is the hybridization? That is sp3. Whew. Now we're on to our last one. I'm going to scroll this up a little bit just to give myself some room. So BRF3. So we're going to have 4 times 7. That gives me 28 valence electrons, right? So bromine and fluorine both have 7. I'm going to go ahead and put my bromine here in the center. I'm going to add 3 fluorines. I'm going to go ahead and start adding some of those valence electrons. So now we have used 24 of 28. That means we've got 4 left over. They're both going to go on the bromine. And so now, how many things are connected to bromine? 5 things, 3 atoms, 2 lone pairs. So that is a trigonal bipyramid. And so now we can draw that structure where we have our bromine here and we see this compound. So in this case, there are actually 2 equivalent structures. And so I will show you both of them. So I'm going to start by creating my fluorines here. And so this structure is called T-shape. You might have also been taught that what we should have done is allow our lone pairs to be as far apart as humanly possible, or compoundedly as possible. And that would be to actually put all of your fluorines here on the equatorial plane. For the purposes of Gen Chem 1, these structures are somewhat equivalent. For the purposes of real chemistry, they are not equivalent. And so which one is the lowest energy conformation is kind of a complex calculation. So I would actually accept both. And so this one is trigonal planar. So for the next compound, which acts about polarity, so bromine and fluorine. So fluorine is 4.0 and bromine is 2.8. So this is a polar bond and it goes in this direction. So the reason these compounds are slightly different has to do with whether or not they're polar. So in this compound here on the bottom, I'm going to use a blue drawing. It turns out that this is not polar. And it is not polar because all 3 of those pull in the same direction. If we look at our T-shaped, we see our axial are polar as well as our T-shaped, but the top and bottom cancel each other out. So the T-shaped molecule is slightly polar. So this is a really great example that the structure of the molecule can determine the polarity. So in this exam, if this was an exam question, I would likely accept both answers. There is a right answer, and it turns out that answer is the trigonal planar, but we have not overly talked about whether or not the axial or the equatorial are preferred and when. So I would accept both. So the last part asks us what the hybridization is, and this is sp3d because all things that are trigonal bipyramidal are. And so I'm going to move this back down and whoops, make it smaller. So when we look at these, this type of table is very complex and it takes a long time. We want to make sure that we can count valence electrons. We can determine where they should go. Well, I did want to remind you that for the polarity, as you saw in your equation sheet, I will give you the electronegativity table. So you just need to know which values, the differential. So if you looked at all of these, I subtracted them. Polarity is determined based on all of the difference between those.